really good to hear. I just had a couple of observations I jotted down this morning. It was really good to hear some of the work that Marcus and his team are doing in this space, and really good to hear some of the plans for the future. We know that there's so many graduates coming out of sports science in Australia and other countries for that matter that they're all going to be looking for employment, so that's really pleasing. And they've already done that, obviously, with their growing staff at the moment. The other thing, just observation I had coming in, was there's such a diversity of speakers and attendees, which is really exciting as well. We often don't see that in sports science conferences, so it's really, I'm really looking forward to chatting to people and hearing what they've got to say the next couple of days. So I'm going to be changing tack slightly to Lisa's talk, although there's some things that Lisa mentioned that I'll probably try and work in here, but I'll be talking specifically about machine learning and how it, which is a big buzzword now we've talked about for 5 or 6 years or even longer in sport, but in particular as it pertains to decision making in sport. And I'll specifically talk about organisational decision making rather than those split-second decisions we see in athletes, but there's probably some crossover that you'll see throughout there as well. So probably the last 20 or 30 years ago, we've been inundated with a lot of research and also kind of content in the popular media around machine learning, and in particular how flawed humans are with respect to decision making. So the kind of really big increase in attention on behavioural economics has been a main part of this, and we've heard how biased we are, how flawed we are when it comes to being objective. All these different types of narratives have come into the public consciousness a lot more than it was before. And I'm a little bit, probably, if you're anything like me, you're probably a little bit sick and tired of hearing about that. And hopefully my talk today helps you to change that narrative somewhat in your own mind and actually look at this kind of area in a little bit of a different way. And especially it's because there's a lot of evidence out there that suggests that humans and machines aren't really well suited for the same type of task. And again, that's hopefully a takeaway that you get from the talk today. Probably a person that put this a lot better than I can is the really famous Rand statistician from, probably late 50s, this comment, or this quote, Merrill Flood, who's no longer with us. But he even identified way back then that computing and machines would overtake or replace a lot of the decisions that are being made by humans, and it already has in many parts of our lives. And he looked at it in a different way. He looked at it by allowing us to hand over decisions to machines would allow us time and incentive to focus on learning to live well together. Now, I'm not as altruistic, but the point is it's giving us more time to work on things that we want to work on. So if you're into data, which most people in the room will have some interest in, then this talk, the first point here today is hopefully for you, that I'll talk specifically about how machine learning can be used to improve decision making in sport more generally. Now, if you're not particularly into data and numbers, and that's fine as well, the other message you can potentially take from my talk is how machine learning and understanding of very basic components of how it works and how it operates can help you to change your philosophy about the way that you frame questions that you're facing in your sporting organisation. So hopefully there's something in it for everybody today. So a little bit of background before we go into the main content and the presentation. I'm going to do a little bit of a sales pitch about why we actually need machine learning in sport. So at the moment, it's like we've always had in professional sport and any sport for that matter, there's drivers and problems. And most of the drivers in sport at the moment are relating to technology and resources. And so as a result of that, we've got more data than ever before. We all know that. And generally speaking, we've got better quality data as well. And that combined with more university graduates, more money being spent on sport, is equaling more personnel and more resources altogether. And of course, all these methodological problems that we're facing in sport, like complexity, bias, I've already mentioned, framing the question appropriately, they interact with these drivers. They don't necessarily cause them, but they do interact both ways. Now, the only real way that I've found we can overcome these problems and drive and harness them together to make any sense is via machine learning. And I'm certainly open to ideas if there's other ways that people have of dealing with these, but in my experience, this is basically our best solution we have at the moment. So if we want to focus on really complex questions that we have in our own environments, and here's an example of some really pervasive ones in the literature at the moment, and in the field for that matter, we're really going to need to engage either machine learning as a way of thinking or as an actual application in order to make sense of them and move the area forward. So in my talk today, I'm going to focus on 4 specific problems that we're facing. And for each problem, I'm going to talk about very quickly how it was identified, where it's come from historically, why it's relevant to us in sport, how machine learning can help, and then lastly, I'll provide some practical examples from either literature or my own work. So before we get into those specific 4 problems, it might be worth us talking about what decision making actually is. And this isn't particularly trivial because there's different definitions depending on who you talk to and what you read. So if you go to a dictionary, you'll see something very similar to this type of example, this type of definition, should I say. Now the orange areas here of emphasis are mine. I've highlighted those myself. So you see things around actions, alternatives and solutions. Now if you read the decision sciences type literature, cognitive science, for example, or psychology, you'll see a definition much more closely aligned with this. So cognitive processes based on beliefs, which then result in actions. And if you look at decision sciences literature, decision systems literature, you'll see something closer to this, which is much more tied up with a computer science-based definition of how we would view decision making. So rationalism, optimal solutions, consideration of all relevant information. And because we've had so many different people working on these types of questions relating to decision making, we've seen it investigated from a number of different perspectives as well. We've looked at the role of time on decision making, the level of importance, how that changes the way that humans make decisions. And of course, this also provides us a bit of a framework in which we can actually allocate a specific decision on these continuum. And so this is something that we try and operationalise in some of the problems I'm facing in a workplace as a way of prioritising which problems or which decisions I should be spending most time on in my own work and in the work of the organisations I'm involved with. So, with that out of the way, let's go into the first of the 4 topics I'd like to speak about. The first one is one I don't want to spend a lot of time on because it probably contradicts my opening statement, but one of the main problems I see in the field at the moment is confusing domain expertise with decision-making expertise. So what do I mean by that? In a nutshell, I mean because someone is a good coach, a good administrator, a good player, a good practitioner, does not mean they are a good decision maker. So another quote, again from the 50s. Paul Meehl, famous psychologist, probably the first to really look at differences in subjective decision making with that of an objective statistical model. He was extremely strong in his wording on this particular problem. He felt like that humans were irrationally expending energy on prognostic jobs that could be done better using complex statistical methods. Bearing in mind this is nearly 70 years ago. Have we progressed a lot from this? Probably not. Now, even though I said I wasn't going to talk about humans versus computers in the start, I'm mindful I might need to convert a few people in the room. So here's an example of one meta-analysis from about 18 years ago, published in looking at basically the decisions of humans versus the decisions of very basic statistical models on various problems in each of these areas. So this little word cloud indicates most of the studies that were involved in this meta-analysis. So there's about 140 papers in this particular example. And in 94% of the cases, the objective models completely outperform the human exports. And I quote this study because it's quite a seminal one, and you might be asking, well, how does this relate in sport? It doesn't really matter what the discipline is. These results are generally replicated all the way through. Now, the interesting thing about this particular study and other meta-analyses that have been undertaken is most of those studies that were used to compare with the humans were fairly basic, either objective models or very basic statistical procedures that have been undertaken. Now, this particular analytical diagram, there's heaps and heaps of different versions online. I've forgotten probably where it even originated. So if we consider that most of the tests that were included in the previous meta-analysis were probably around that database query or statistical model area, not even getting into the machine learning space, we can only imagine at how more exacerbated that divide between humans and machines is going to become in future. So, if we run this meta-analysis again in another 10 or 20 years, the results might be even more conclusive. But as I said in the introduction, I don't think this is a problem. If we think about the people that are in the room right now, and I think most of us would fall into one of these 4 categories, or maybe academics is one I've missed off there. If you do this as a thought exercise in your seat right now about what are the first 1 or 2 words that come to mind when you think about the best coach you know, or the best player, best practitioner, I'll let you do that in your own minds at the moment, and I've got some I prepared earlier. You might agree with some of these, you might have different things that come to mind firstly, and that's fine. But decision making is probably not on the first couple of things to come to mind when I think about the best coaches I know, or the best players I know, or the best practitioners. But that is a problem because these particular people have various decision making functions that are inherent in their role, and they're very important to their role in order for them to be successful. But the reality is that most people actually haven't had a lot of training unless they've formally sought that type of training in their education or their experience growing up into those actual roles. So, as a bit of a summary for this first section, we shouldn't expect our coaches, our practitioners, to be decision-making experts. And if we do, we're probably being harmful to our organisation on 2 fronts. Firstly, they're going to be suboptimal compared to a machine. And secondly, by diverting their attention away from what it is that makes them a good coach, a good practitioner, is actually taking time away from that and moving it on to something that could be done better by a machine. And secondly, machine learning isn't perfect. But as we see throughout the next couple of slides, it actually doesn't need to be. It just needs to be better than what we've got in place at the moment. And the other thing that's important to note is it's going to be generally better than other forms of analysis that we've been using now or been using in the past. Okay, second part of second problem, should I say, relates to framing the question appropriately. Another quote. Charles Kettering, the engineer responsible for putting the ignition in your car. A problem well stated is a problem half solved. And hopefully you'll see why that statement is relevant on the next few slides. Let's look at a really pervasive one in sport at the moment to unpack this kind of idea of framing the question appropriately. Let's look at training availability. It's pervasive, it's on everyone's minds in a professional sport at the moment, and for that matter, any type of sport. When we ask ourselves whether an athlete is available to train, depending on the person asking that question, they could be asking that in a completely different way. So if we have a glass half full person, maybe it's a coach, maybe it's the athlete themselves, they're probably focusing mainly on what improvements they can get in a given training session. People that are designed to be more risk averse because of the nature of their role are going to be looking at it more with these types of questions. Are there modifications that are required in this session in order for the athlete not to be injured? What level of injury risk is there? So having this explicitly stated before we start to look at this as a problem is really important, and it sounds extremely basic, but it's not done often enough. Now, the other consideration in all this is how we actually represent the dependent variable in a question like injury, like training availability. So in many places, or many people that I speak to, the concept of injury risk and training availability is one and the same. Now, whether that's right or not is a conversation for another day, but the idea of manipulating that dependent variable completely changes the way that we face this particular problem. So if we look at the idea of training availability as injury risk, we might have a number of different scenarios whereby an athlete presents with a level of risk on the y-axis here from 0 to 100%, and we might have a prediction of around about 10% with a corresponding confidence interval. We might have a second situation of the same athlete or a different athlete where there's a little bit of a higher risk, and so on. And we might have the same situation as the third one there of the same athlete with a wider confidence interval associated with their injury risk. Now, how we actually operationalise this particular concept of injury risk is a question that hasn't been particularly well answered yet. And so invariably what ends up having to happen is we have to make a decision around how much risk are we willing to absorb before we change our decision. Now, because we're humans, we like to actually make this decision easier for us. So what we ended up doing is kind of coming up with something like this. We call one green, one orange, one red. And we say that one situation is acceptable risk and one is not. And that tends to be the way we make sense of something like this. But then, of course, there's all these other questions that come alongside that, like the eye of the beholder. Who's actually making the decision from this type of data? So, for example, I don't have any data to support this, but I would hazard a guess that someone working at a professional club with very expensive players is likely to be more risk averse than someone who is working at the community level. Maybe someone can do that study. So if we change the dependent variable again to something around a classification of someone being injured or not, then we get different results yet again. And you know, we've all seen something like this in the literature at the moment, where we have this idea of a sweet spot or a danger zone. Again, we make this kind of arbitrary classification about what's safe and what's not. And that's another way of us to actually make sense of the question we're facing. But again, this reduces the dimensionality of our data and allows us to prescribe more easily, but it also is going to result in a lot of false positives. And what I mean by that is we're going to be pulling a lot of guys out of training that are otherwise safe to train. Not such an issue in some disciplines, but in sport, pulling athletes out of training all the time means they're going to be progressively detrained, of course, and there can be the corresponding injury risk with that. The good news is people are starting to pick up on this in the literature, and Dave Carey and colleagues, I've only found this literally a couple of weeks ago. But Dave represents probably an example of what I call the new breed of sports scientists, people that are working in data science, coming into sport and starting to have an impact on how we understand these questions. These, frankly, less sexy questions, but more important questions with respect to the methodology on how we handle these problems. And of course, we can look at the approach, well, look at this question in a number of different ways. We can look at it from a rule-based perspective. You know, the last time we saw this combination of factors, the athlete got injured. We can look at it how players cluster together in their behaviour. And of course, when we particularly have very poor data or very low volume of data, there is always the chance that just the basic intuition of the practitioner will outperform any objective model we've got altogether. So just the basic heuristic might work better, and just our intuition. And I won't talk about intuition at all today, but those that are interested, certainly the work of Gary Klein and Gerd Gigerenzer is worth checking out on the role of intuition in decision making. Now, why have I gone through this really large kind of examination of training availability? I'm not beating up on training availability, by the way. This is just an example of one question. Well, it just so happens that if we look at machine learning and the families of algorithms that exist within machine learning, each of these particular families are capable of handling that question that we just looked at in different ways. So we certainly don't have time to go into the main differences theoretically about how regression differs to classification, to rule-based systems, to clustering, but I'm going to provide a different practical example on the next couple of slides, which hopefully makes it a little bit easier to digest. So let's change tack away from injury prevention and look at team selection and look at it from a coaching perspective this time. If we look at regression approach to team selection, we'd be looking at the idea of trying to predict something on a continuous scale. So, for example, the performance rating of an athlete, just like Lisa's talked about in her last presentation. So here's some data from 2017 with the Western Bulldogs. No surprises about who's at the left-hand side of that graph. These are the AFL rating points on the left-hand side, publicly available data. A regression approach to picking the next player in this team, if we grey out those players that weren't playing in a given game, we would select the player next in line, so to speak, the highest performance rating for that particular player, and we would bring them into the team. So that's how a basic regression approach would work. Now, if we turn this into a classification approach, we actually need something different. We need something additional to that. So let's say, for example, we want to actually look at a specific position and we want to pick a forward for the team. All of a sudden we can't pick the blue player anymore because he's a midfielder, so we need to pick the best available forward, which in this case changes our decision and means we have to pick the player further down the line on the graph. If we use a rule-based machine learning algorithm, and interestingly I think this one probably is the closest to the way I see coaches make decisions intuitively in the field, but I'm interested in the thoughts of others on this. We have these kind of requirements in our head, and in this case, in an algorithm, that inform us on whether we should select a given player or not. So these are just some examples. We might want a specific height and weight of a player. We might want them to fulfill a certain amount of training before a match, and we might want them to be performing really well. And then we can compare players against each other. Do they get a tick or cross in each of those categories? And the one that fulfills the most or has the most ticks, we end up selecting for a given game. And of course, the other option is we're trying to replace what we'd call a like-for-like player. We look at how players cluster together in their performance criteria. Here's an example from a paper from one of my PhD students earlier this year, in fact, looking at how players cluster together in the Australian Football League. This is for the Adelaide Crows from 2016. And the closer these circles are to one another indicates their level of the closer similarity they are in the way that they play the game. The colours represent the position they actually play, and the size of the bubble are the actual quality of the player, the performance of that player over time. And you'll notice, astute viewers will notice that some of the colours there are mixed up. So we have players that look very similar to one another in the way that they play different positions. So how we use that data for those purposes is interesting, whether they can play multiple roles or should we be changing the position that those particular players play. So ideally, we might actually come up with a meta approach to this solution, and we might actually get a recommendation from all 4 of these machine learning systems, which, based on the voting, on which player gets the most number of votes, we end up with a situation where we go with player A because 2 of the systems recommended that to occur. I'm not familiar with anyone using something like this, but this is potentially where it could go in the future. Now, the issue with this is, of course, each of those dependent variables, as we talked about earlier, are they're different in the way that we express them. So they're not actually directly comparable with one another about which is the best solution. And we also know that the way that we evaluate a decision or one of these types of models being implemented in the field is more than just about accuracy. So it's more than just the accuracy or the error inherent in our model. So if we go back and re-evaluate all the times we used a rule-based solution, did we have a good performance by the team? It's more than just that. We also need to look at what it compares to how we picked the team in previous years. Is it an improvement over what we've done in the past? And then on the left-hand side of this diagram, it's particularly important around the human component of this, because whether we like or not, humans are what we're dealing with in sport. So what's the feedback from the coach? What's the feedback from the players even and other staff about how the solution works? How is it operationalised? And then the feasibility is just as important. If the process is very slow, it's cumbersome, it involves too many staff, then there's also a possibility that it's never going to see the light of day in an applied environment. And certainly within reason, but in my experience, feasibility takes priority over the precision of the model every time working in the field. And so if we pull these things together, the accuracy, the error, the feasibility, we can get to a situation like this where we can directly compare our classification approach with our regression approach. One might work better than the other with respect to accuracy, but one might be more slow, or one might be less feasible. Sorry, you probably can't see the white from the back there. So in summary of this particular section, remember to question the question. So machine learning is not just a tool that we have at our disposal. It can also be viewed as a framework or a philosophy for the way that we frame the same question in different ways. And the way that you decide, or the type of method that you end up deciding to use, will depend on its operational compatibility. So if you have a fantastic machine learning system or decision-making system that looks great on paper but can't be operational in the applied space, it's practically useless. And thirdly, we should evaluate our decisions using a framework rather than just on the accuracy of a model, but also on these features that we just spoke about on the previous slides. Okay, into section 3. Not a term that we see discussed a lot in sport, and born out of psychology, again, many years ago. Let me try and explain it in the context of sport. When we make decisions, either as a model or as a human, these are bounded by certain things that we have to face in our environment. Let's look at a couple of examples. We're bounded by time. I think we can all experience this or have experienced this in our own environments. Sometimes we'd like more time to make decisions that we have to make as practitioners or as coaches. We're limited by our own ability to process information, and I'll talk about this a little bit later on. Even computers can be limited by our ability to process, particularly vision, for example. We're limited by access to information. Sometimes when we're making decisions in our roles, we'd like to have information, but we can't actually access it. We don't have time to access it, or we actually don't have the ability to get it for various reasons, maybe cost, for example. And then, of course, the old Donald Rumsfeld unknown unknowns. We don't know what we don't know. So, for example, there's things out there that matter to our decisions that we're making that we don't even know that exist yet. And I think we've all seen evidence of that in the last few years as technology is absolutely going through such a major rate of change. There's things we're going to be measuring, and I think Lisa's point around the psychology or the psychophysiology of an athlete is probably one of those that we're just starting to realise just how important that is, but we probably can't really measure it that well yet. So the example I use on this one, I'm always kind of hesitant to use it, is marriage or choosing a partner. We have a certain amount of time on this earth to choose a partner that we want to spend the rest of our life with. We spend a lot of time processing information on that person, and some of that we don't process to decide whether we want to spend time with them or not. There's access, there's lack of access. Sometimes the person we want to spend time with doesn't actually want to give us all the information on them. And then, of course, there's going to be things there that we never actually ever learn about our partner to the day we die. And the way that humans make decisions around this is on the level of how much they satisfy them. So not satisfy, but satisfice, which basically refers to humans deciding and pursuing a course of action that satisfies the minimum requirements necessary to achieve a particular goal. Probably not best to refer to the decision that you made to spend with your partner in that way when you're talking to them, but that's actually quite an accurate representation of how we make that decision. So Herbert Simon, the psychologist who was responsible for really starting off this inquest into bounded rationality, and again another quote, which is important to keep in mind on the next couple of slides, that because we all access information differently, we all have different level of time to make decisions, in our own minds we're all behaving rationally with respect to that information set that we have at our disposal. And so when we consider really pervasive problems like training availability, it's important to keep that in mind, that when you're making a decision compared to another practitioner, you might be using a completely different information set in order to do that. So the best way to represent that is something that I find it quite useful at least, hopefully you do the same, is if we consider, again, let's go back to training availability as a concept here. If we consider all the information that we measure on our athletes inside this circle, and these are just some examples, obviously this isn't comprehensive, but we look at their load, we look at their wellness, their screening data. We would all agree there's information that sits outside of this that we would like to collect. So in our case, it might be something that's at the Western Bulldogs, it might be something quite expensive we'd like to do, but we can't afford it. I mentioned psychophysiology in the last couple of minutes, that's probably another example. Genetics, all these things that either we can't afford to measure or we don't have the time. And as I kind of alluded to a couple of slides ago, that results in this situation where we kind of, depending on how we chop the data up, how we model it, how we represent it, we can almost end up with plausible and equally contradictory principles based on the analysis we've undertaken. Now, if we revisit this earlier slide around this explosion of data and better data, we know that these inner rings of this circle, or these inner circles here, are going to continue to expand out because we are going to have more information coming at us and we're going to be able to collect it. It's going to become cheaper and easier to collect. We're already seeing that starting to occur. So a bit of a challenge for these guys at Fusion is to obviously account for that type of data, and particularly vision type data where it's such a large size. And it might not be lost on some of you in the audience, the overlap here with the Dunning-Kruger effect. You've all seen this slide before. What we think we know, what they actually know. But bounded rationality fits quite well into this diagram as well, because we've got a third line that we can overlay here, which is actually, I'll go back, how much I realise there is to know. And as we start to delve into problems deeper, as we become more expert in areas, we realise just how much more there is in that outer circle that's going to continue to grow over the next couple of years. How does this work in practice? I normally let this run when I speak internationally, but I think most people in the room have seen a game of Australian rules football. This is a behind the goals view that we'd use for analytical purposes, not typically seen on the television. And of course, we then, like most sports these days, we then model that data, positional data, to try and make sense of what's going on in a particular game. So I'm going to switch tack again a little bit here. I'm going to talk about the notion of evaluating a player now. So moving away from training availability and moving away from team selection. So here's an example of some work that we've been undertaking with one of the partners at our university on evaluating the quality of a pass in Australian football. And the principles are really quite transferable to any team sport that involves manipulation of space and time. These blue dots here represent our team with the possession of the ball, and the purple dots represent the opponent. Now the darker green areas here are basically where our model is recommending the person move the ball based on minimising the risk of that particular pass and maximising the reward. But as we change the information that's included in this, as we add information to the model, the picture starts to change. So in this particular example, we've actually started to add the velocity of the players, every player on the ground, and the orientation, the way they're facing, whether they're facing towards the ball or away. Because obviously, if we're running quite fast in one direction, it's not very easy to turn all the way around and run back the other direction. But you'll notice that those dark green areas are starting to change now. If we add in the constraint of the player's skill, their empirical data on their skill performance over time, the picture shifts again. And if we model the velocity of the ball and the time it takes for the ball to move from point A to point B, again, not only has the picture changed slightly, it's absolutely changed completely. And so we tie it back to the introduction of this particular section. By adding more information, we haven't actually made just a better model, we've actually made a completely different model. And in this particular case, the practical output of this type of work is as follows. I mean, those red dots there represent every kick that was included in our particular model here. Now on the x-axis here we have distance of the kick, and on the y-axis here we have the improvement in equity, so basically the quality of the disposal. Now the blue dots here represent what the model recommended where the athlete should have kicked the ball. So on average, the kicks that were included in our model were about 26 metres in length, and they improved the equity of the team by about 0.25 points on a standardised scale. If every athlete had followed the model recommendation, which we know is extremely unlikely and improbable, they would have been kicking the ball a lot longer, on average about 35 metres, and it would have improved their team performance by quite a lot more. And any followers of Australian football at the moment would know that the game is inherently quite conservative at the moment, particularly the way it is coached. So this kind of, the face validity of this makes a little bit of sense. And so kind of a takeaway would be that passes should be longer and less conservative. But if we look at the evolution of that particular model, we know that it's never going to be perfect. We might find new information, and you can probably think of some in your own head sitting in the audience now, other considerations we need to add to that model to make it better, and it might change the actual outcome altogether. So in summary, the more good quality data, the better. I kind of reject this notion that we've got so much data we don't know what to do with it. I don't think we've got anywhere near enough good quality data to actually answer a lot of the questions that we want to answer. But the only way we'll be able to handle that is via machines. All models are biased, whether we've developed the models ourselves or whether they're just, whether we're making a decision ourselves or whether they're based on machines. We've got to insert that information into the machine. And the way we do that can be just as biased as it can be when we're making a human decision without the intervention of a computer. And then the main takeaway here is it's not about being perfect, it's about being better. By implementing that model I just showed you, we are definitely going to be able to improve the way that an athlete kicks, the way they move the ball. It might not be perfect, but it's certainly better than existing practice. Last section, interpreting complexity. Another graph for you. X-axis, we have some items on a particular problem. Let's come back to training availability because I think that's a particularly pervasive one. And if on the y-axis here we have this hypothetical situation where we have all the information we would ever want to know on a particular problem. The way that we normally undertake a decision-making process in our own environments is as we add items, as we start to add information to a problem, let's say training availability, we look at the GPS, we look at the wellness, we look at the screening. Theoretically, that should help us to increase our understanding of that particular problem. Now, we've talked about the limitations of humans with this particular issue already, but some of you will be familiar with, again, very old work around Miller on the magical number 7. We know that most people can only really recall about 7 pieces of information in their short-term memory before they actually the eyes start to glaze over a little bit. Interesting side note there is some research on this that it is an ecological adaptation, that particular trait of humans, that we intentionally forget information beyond 7 pieces because otherwise we're going to experience constant paralysis by analysis. So that's again another area for future research, particularly by people in cognitive science. But we also know that as we start to add more pieces of information towards the back end of that particular problem, the information doesn't contribute as meaningfully to our understanding of that particular phenomena. Here's an example of this in a very recent example, excellent paper from a group out of Italy that compared how particular football pundits in the media rate the performance of an athlete in a particular Serie A football game. Now, the way to interpret this graph is the writing on the outside of these circles are all different performance indicators that you would normally see reported in a football game. And the spikes on the inner area moving towards the outside indicate that they are the things that the actual pundits were focusing on when they were giving their ratings for the athlete. And this is a striker, you can probably work that out because basically almost the entire rating for those particular pundits were based on the number of goals that they scored. So it illustrates a couple of things, that we probably don't need all these performance indicators if we're going to use a human to make judgments. It also probably indicates a little bit of a bias of those pundits to just focus on 1 or 2 things, but it also focuses on the magical number 7 that I introduced on the previous slide and provides evidence of that phenomena. Now, the other consideration here is this notion of parsimony, because as we start to add more and more pieces of information, we get a very complex, probably sometimes needlessly complex model. So the notion of parsimony is obtaining as good a result as we can with as little information as possible. So when do additional items stop contributing meaningful information to our particular problem? That's the kind of headspace we're in when we're facing an issue of parsimony. Here's an example from the literature about predicting how far someone can actually throw a javelin. Now, you can't read those items, and that's somewhat intentional. These are all different parameters that were fed into a neural network in which they were trying to do a talent ID expedition and try and find out who would throw the javelin furthest in the actual Olympic Games. I think it was out of Poland, this study. Now, the interesting thing about this is not only is this not a particularly parsimonious solution, but it's also what we'd call an overfit solution, which is basically explaining a situation so specifically that it never generalises to another. So if this model works really well and we can predict how far someone will throw a javelin, the problem with that is we need to go next time and get all the same information, and we need to test every single athlete on those pieces of information in order to get the same solution. So the idea of parsimony, and the athlete, and in this case the authors actually recognised this, that with those 5 variables on your screen now, they almost had the same quality model. They were able to explain about 82% of the variance in how far someone would throw a javelin using just those 5 parameters. So a classic case of where in the most parsimonious solution, the one on the right, is almost as useful as the one on the left with using much, much less variables. If we look at this from a skill perspective, the justification of how we include variables into the model, we normally use a constraints-led approach to this particular problem. And I think most of you in the room will have seen some variant on this over the last couple of years. It's particularly popular now in a number of different disciplines in sports science. So we look at things that are affecting the individual, the tasks they're undertaking, and the environment. And the challenge is obviously how these variables interact, which we'll talk about here just to finish off. So if we look back at our piece of vision that we saw earlier, and we look at Dale Morris down in the right-hand corner kicking the ball, we know that some of those constraints that we would use under that model, like the target, we could look at the pressure, we could look at his level of fatigue, the time, we could go on and on. We can keep adding constraints to that model. And that helps us to explain how and why the athlete actually chose to kick the ball where they kicked it. And the way that we tend to do this is using one of the machine learning families I've spoken about already, which is association rules. Now, association rules is almost 40 years old now as an algorithm. So we sometimes think about machine learning being quite new and cutting edge, but some of the basic techniques are very, very old. They're older than me. So in this particular case, the origins of association rules, seems a bit abstract here, but comes from market basket analysis, analysing what you put in your trolley at the supermarket. And it works on two particular factors, what we call support and confidence. And of the first one, the way we would view support in this market basket analysis perspective would be around this concept of milk. How many times when someone goes to the supermarket do they buy milk? If it's 7 out of 10 times, then we would say there's 70% support for that particular rule. But where it gets a little bit more complex is when we look at the confidence. And the confidence relates to not only just the milk, but how many times when people bought milk did they also buy bread or buy eggs or buy toilet paper? And that relates to the confidence of the actual rule. And these types of rules are all around us. I went to buy a book not long ago, and of course, like all of us that have purchased something through Amazon, you'll see all sorts of rules come up and recommendations. This is just an example of an association rule algorithm telling us what we should buy based on what others have done. So how does this work in practice? Well, if we look at some transactional data from a game of Australian football, you've all seen something like this before. We have a timestamp and an event. Most of us would code, or most of us who work in performance analysis anyway, would code those events with corresponding characteristics. So maybe the field position and maybe other constraints that I spoke about on the previous slide. So what pressure was the athlete under, how much time do they have, and how fast were they running, for example. And of course, I've put this little arrow on the right-hand side because that could go on forever and ever. So if we look at a practical example of how that association rule algorithm could work, the support in this case for high pressure in our data set here of 4 instances is 2 out of 4, because 2 of those 4 instances we saw the athlete being under high pressure. The confidence for high pressure and short time would be 2 out of 2, 100%, because every time the athlete experienced high pressure, they also had no time. And we can follow across the screen and down the screen, so a depth and breadth approach to the particular problem. Now you might say, well, that's pretty easy, I can just go through my timeline and have a look at that, but of course the real value of this is picking out what happens a lot and what happens in combination with one another when we have a number of instances involved in this particular model. And so the way we've used this at the Western Bulldogs, for example, is to not only just focus on those commonly occurring and predictable occurrences, but also use it to describe the conditions of competition. So how we actually know what competition looks like. And of course, if we know what conditions a players experience in competition, we can help to identify their strengths and weaknesses. It also allows us to design training environments that replicate or don't replicate, depending on what we want, competition. And of course, if we add an outcome to that measure, so for example, we add expected points or performance, any performance metric of interest on the outside, we can also look at which conditions are best related with producing a performance outcome of interest. So in summary, comparing humans versus machine decisions is like comparing apples and oranges. They utilise different information sets. That's just probably harking back to the section 3. And secondly, whilst we should embrace complexity, we don't want to throw out those complex interactions between the constraints we experience in our environment. We should also strive for parsimony. So in conclusion, coming back to those first 2 aims I had for the presentation, hopefully I fulfilled those to some extent, and thanks for having me.